All right, thanks for the invitations. This is based on a paper that came out last December, as well as another paper that came out the year before. All right, so this talk is about string theory, in particular, non-perturbative approaches to string theory. So the only non-perturbative definition of string theory that we have is from holography. So the classic example is that type 2B string theory at 85 process 5 is dual to 40 super Yang. So in this correspondence, you relate the string parameters, which is the string length and the complexified string coupling, to the corresponding parameters in the CFT, which is the complexified gauge coupling, as well as n. Another classic example of ADS-CFT is where you have M theory in ADS4 cross S7 mod CK, and this is dual to a three-dimensional CFT called ABJM, which is a Chern-Simons matter theory. And so in this correspondence, because it's M theory, you don't have a string coupling anymore. Instead, you only have an analog of the string length, which is actually 11-dimensional Planck length, and that's also related to n, according to this dictionary you see here. The salient feature of this duality that we're going to use is that graviton scattering on ADS is dual to the stress tensor correlator in the CFT. So you might think that ADS-CFT kind of solved the problem of quantum gravity in ADS. But the truth is that it only solved half the problem, in that it translated the very hard problem of quantum gravity into the slightly less hard problem of CFT. But the CFTs that are dual to quantum gravity are strongly coupled. So we still don't really know that much about them. So it just turned one hard thing into another hard thing. And so to truly say that we understand quantum gravity using holography, we have to also solve the CFT non-perturbative. So there are some partial results that already exist in the literature. So for instance, if you look at these CFTs when n is large, which on the string side is dual to the classical string, then there's this method called integrability, which allows you to study quantities for finite Tuft coupling lambda. But this method only works in the planar limit as n goes to infinity. We don't yet know how to use it for subleading orders of 1 over n, and so particularly it can't be used to study the quantum string. And then for the case of M theory, where the coupling is always strong, there just is no integrability. And so we can't get anything from integrability in that case. Of course, for a gauge theory, you can always study it at weak coupling using Feynman diagrams, like in some of the talks earlier today. But that doesn't really tell you anything about quantum gravity, because gravity, is only really manifest at strong coupling. That's the context in which you see Einstein gravity. At weak coupling, you just see some incredibly stringy theory, which doesn't really have any intuitive interpretation. So in today's talk, we're going to combine the three non-perturbative constraints, which I think are the only non-perturbative constraints, in order to numerically study holographic CFTs and thereby non-perturbatively study quantum gravity, thus completing the dream of ADS-CFT. And so these three constraints, the first one is unitarity, which manifests in this context as the fact that OP coefficients are real and that scaling dimensions are bounded. The second constraint is crossing symmetry, which comes from conformal symmetry and which can be combined with unitarity in order to make the conformal bootstrap algorithm. And the third non-perturbative constraint is supersymmetric localization, which allows you to input certain protected quantities that depend on the couple. And so it's really only by combining all three of these non-perturbative constraints can you actually non-perturbatively solve the theory. So like any subset of them would be insufficient, as we will discuss. Okay, so let's first discuss n equals first Bragg-Mills. Afterwards, we'll do ABJM. So this is the earlier work from a couple years ago. Afterwards, we'll do the more recent work. So some basics about n equals 4 CFTs. So all such CFTs have an SU4R symmetry and are conformal manifolds with one complex parameter tau. And so in particular, you can define these theories by the value of their central charge, which in the case of Lagrangian theory is the dimension of the gauge group divided by 4, as well as the complexified coupling. So the only actual known n equals 4 CFT is n equals 4 super Yang-Mills. It might be the only one. And it's a gauge theory with the matter transforms in the adjoint of the gauge group G, which must be a compact classical Lie group. For this talk, we're just going to assume that G is SUN, although the methods would work for any other group. We could do SON, for instance. And so in this case, C is proportional to n squared. So we'll use them interchangeably. So this is a conformal manifold, which means that there is a duality group, which moves you along the conformal manifold, it's SL2Z. And two special points on this manifold are when tau equals I or when tau equals e to the I pi over 3. Because in this case, the global symmetry is enhanced. Okay, so the quantity of interest that we're going to study is the stress tensor 4-point function, because this is dual to graviton scattering in the bulk. And so we can use symmetry to study the superprimary of the stress tensor multiplet, which is a scalar in the 20 prime, which we call S. And then, as usual in any CFT, you could expand the 4-point function in blocks. And so there are different multiplets that appear in this correlator. The protected ones are trivial, and they're all resummed in this term called G protected. It's trivial in the sense that it doesn't depend on the coupling. So you could just fix it from the free theory. We don't really care about it. All the interesting aspects of this 4-point function are in the long multiplets, which is what we write here. And it turns out you can actually exactly solve the constraints of supergrid formal symmetry by basically writing some kinematic factor. And then everything interesting is then in the sum over long multiplets. So in particular, the goal of studying this 4-point function is to study the scaling dimensions delta and the OP coefficients lambda that appear for these long multiplets. So let's discuss the first non-perturbative constraint, which is crossing symmetry. And this follows from the fact that we have a Euclidean CFT, so you can just rearrange the operators on the left-hand side, and the right-hand side should be invariant. But this gives a non-perturbative constraint, because basically these blocks change when you exchange x1, x2, x3, and x4. So this gives a whole function's worth of constraints on the scaling dimensions and OP coefficients. These constraints you can combine with the fact that the OP coefficient squared must be positive in order to create a system of equations, an infinite system of equations. There's an algorithm of how to truncate that to a finite system. I won't go into the details. This is the numerical bootstrap algorithm. But the point is that this was first implemented by these authors roughly 10 years ago to get upper bounds on scaling dimensions and OP coefficients for each spin, where the spin has to be even in this case. But these bounds for the paper 10 years ago were computed just as a function of c, which remember is related to n squared. They did not know how to compute these bounds as a function of tau because we're taking a very axiomatic approach. We're not using a Lagrangian so far. And so nowhere in this axiomatic approach have I told you what the value of tau is. So of course, in principle, the scaling dimensions and OP coefficients depend on tau, but because you don't know exactly how they depend, there is no way of inputting those values. And so that was the limitation of the paper from 10 years ago. So before we talk about the new approach, we can review some perturbative data. So first of all, you can study this theory of weak coupling, as was discussed in one of the previous talks, just like any gauge theory as we've known for like 80 years. And so, for instance, you could compute one of the simplest observables, which is the scaling dimension of the simplest long multiplet. This is called the Konishi at weak coupling. It has dimension 2 at the free theory. So many people have contributed to computing this quantity. The cutting edge is that we now understand it to 4 loops, which was done by this Russian fellow. One kind of fun fact is that it's planar exact up until 4 loops, where you get the first non-planar correction, which basically follows from supersymmetry. And you could similarly compute the OP coefficients to the same order, which is also done in some nice recent papers. Okay, it's an excellent question. People have computed, I think, the first instanton. There's a paper by Fernando and I think maybe Perchemsky, if I recall. Yeah, so you could compute the first instanton correction also to this data. Although, of course, it's quite small. They might have even had maybe more than the first one. Okay. So another perturbative approach is integrability. This is perturbative in n instead of being perturbative in the coupling. And so this works in the strict n goes to infinity limit, but it works for finite lambda. It's a very powerful approach. The most cutting edge version of it is something called the quantum spectral curve, as proposed by these authors, also roughly 10 years ago. Although, even though it was like written down 10 years ago, it's very hard to implement it in practice. So they only actually implemented it in practice in general a couple of years ago, a year and a half ago, basically. And so just recently, we actually finally have the spectrum from integrability. So using the spectrum, you could compute it for any value of lambda you want. So at small lambda, it matches the weak coupling from the previous slide. At large lambda, you can get this expansion, which matches expectations from string theory for basically some kind of like spinning string solution. But the limitation, as I keep emphasizing, is that this is really only the planar limit. So in the bulk, this is only telling you about classical string theory, which would be like leading in string coupling. It doesn't tell you anything about the quantum string. So one manifestation of that is that whereas single trace operators have this non-trivial expansion we see here from integrability, higher traces just factorize because we're at leading order at large n. So that means if you were to look at the simplest double trace operator, integrability would tell you that the answer is just 4 because it's just 2 plus 2 because you're not sensitive to the 1 over n squared. Okay. So now let's move on to the next non-perturbative constraint. So we've discussed unitarity, we've discussed crossing symmetry. The final one is localization. So it's shown originally by Pestun, I guess 15 years ago. A quantity which is useful to consider is the mass to form sphere-free energy. And so the mass couples to this hypermultiplet, which is part of the stress tensor multiplet. So this means that if you take derivatives of mass and set the mass to 0, then you get integrals of correlators of the stress tensor multiplet. And so this is a purely kinematic fact. So it's non-perturbative. And so we worked out these kinematic constraints in some papers with my co-authors a few years ago. And it turns out there's two independent constraints related to the 4-point function. Of course, for higher point functions, there'd be even more constraints. And so the first constraint involves two derivatives of mass and two derivatives of tau, because tau also couples to the stress tensor multiplet. And then the other one is 4 derivatives of mass. And so these are integrals of the 4-point function, so that means you could write them as integrals of this block expansion, which is what we care about for the bootstrap. Where I2 and I4 are certain integrals you can find in our papers. And so the reason why it's useful to relate the mass to form free energy is that we know how to compute the mass to form free energy using localization, as Pestun showed us. So in particular, you can write the answer, which would naively be an infinite dimensional path integral. It simplifies due to localization into just n-1 integrals, corresponding to the Cartans of the S2n gauge group. So this is the explicit answer in terms of some special functions. And notice that it depends on the instantons according to this Nekrasov partition function, which is some incredibly complicated function, but it's known exactly due to Nekrasov. So for low values of n, you could just do this integral numerically if you want to get the exact non-perturbative answer. But ideally, we want to look at larger values of n because we want to look at the large n regime where gravity is manifest. And so if we want to do that, then we need to find a more efficient method of estimating this n-1 integrals. So the way we do that is that, first of all, if you ignore the instanton term, then it turns out that because when the mass is 0, the matrix model is a Gaussian matrix model, that means you could compute anything in a Gaussian matrix model. And so in particular, taking derivatives of mass and setting mass to 0 is just computing a very complicated operator in a Gaussian matrix model. And so we know how to do that. So I did this in my paper 5 years ago, and the answer you get looks like this. So it went from being n-1 integrals to being just one integral, and then you can just do this numerically for any value of the gauge coupling, which is what this tau2 is. And these L's are Laguerre polynomials. So a complementary method is that at large n, you can actually compute the full answer to any order in 1 over n, including instantons, which is shown in this work here with my collaborator Tsung Kao Wen, who's in the audience. And it turns out that the answer is written in terms of Eisenstein, non-homomorphic Eisenstein series. So I don't know if any of the mathematicians showed up to this talk, but if they did, maybe they'd be interested in these non-homomorphic Eisenstein series. So we now have kind of two complementary approaches. We have finite n, finite coupling, but no instantons, where we know things exactly. And then we also have large n with instantons. So it turns out that you can actually just combine these two approaches to give an extremely accurate numerical estimate for any value of n and tau. And so that kind of solves the problem of computing these n-1 integrals. Okay, so before we talk about the non-perturbative results, just one last example of a perturbative result is that we talk about weak coupling, we talk about integrability, but you can also use holography itself to compute observables at a large n expansion, because then according to holography, this is dual to calculations in supergravity plus higher derivative corrections. So there's this program called the analytic bootstrap, which was first applied to the higher derivative corrections, actually by Polchinski back in 2009, and then later on by Fernando and collaborators in 2014. And so basically, you impose crossing symmetry, which you can solve exactly at large n. And so the only thing it's using is crossing symmetry. You're not imposing unitarity, you're not doing localization. And just from crossing symmetry, you're able to constrain the answer at every order in 1 over n in terms of just a few coefficients. So the leading order term, this corresponds to the supergravity contribution, and this is just completely fixed by these constraints. And in the next correction, this is the r to the 4 correction to supergravity, and this you can totally fix in terms of one unknown parameter b. And then this is the one loop correction, and you also need to fix one unknown parameter. This is the next high derivative correction, now there's 2 unknown parameters, and as you see, that's how the pattern goes. So the higher order you go in 1 over n, the more of these unfixed coefficients you have, and you would need extra data in order to fix this. You would need to know maybe something from localization. So this is what we know from this kind of analytic bootstrap. But the analytic bootstrap, it's not as strong as it could be because it's not using unitarity. Because the constraint of unitarity is trivial when you take this analytic large n expansion. So that is why the numerical bootstrap is much stronger than the analytic bootstrap, because it allows you to impose unitarity. by working at finite n, basically. Okay, yeah, so to fix these b's, we need more constraints. So analytically, you can fix two of them using localization, which allowed us to fix up to the d to the 4 to the 4 term. And so, analytically, you can then read off data up to that order. So the simplest quantity would be this double trace scaling dimension. So it starts at dimension 4. And then here are like the supergravity correction, r to the 4 correction, one loop correction, and d to the 4 r to the 4. And notice that it depends on tau in this non-trivial way, in particular these non-holomorphic Eisensteins. But if you want to go beyond these protected corrections, you need a more powerful constraint. So you need the numerical bootstrap, which works at finite n, which is what I'll present next. Okay, so here are the results starting for n equals 2. So in this plot, the x-axis is the coupling, and we don't talk about instantons here because the effect is so small you wouldn't see it. And then the y-axis is the scaling dimension of the lowest long multiplet. So this would be the Konishi at weak coupling. So you see that indeed it starts at 2, as you would expect for the Konishi. This black is the upper bound. The right-hand side is focusing on this regime of strong coupling. And so here we do show the dependence on the theta angle, and it's kind of sinusoidal, as you would expect from the localization input. And so the first kind of exciting aspect of this plot is that a priori, this is just an upper bound. And so it wasn't guaranteed that this upper bound, would be very strong. It could have been that the physical theory could have been like somewhere over here. But it turns out that if you compare the weak coupling predictions to this upper bound, they lie exactly on the upper bound. And in fact, they lie exactly on the upper bound for a bigger regime than you might have even guessed. Because of course, this is an asymptotic expansion at weak coupling. And so this strongly suggests that this upper bound actually corresponds to physical theory non-perturbative, not just at weak coupling. Another interesting thing you learned from this plot is that you can compare this bound here, which was computed by combining crossing symmetry, unitarity, and localization, to the previous plot, which did not have localization and was thus a horizontal line, because this previous bound from Rastelli 10 years ago didn't depend on the coupling. And as you see, the improved plot is always stronger than the old plot. And so this implies that Rastelli's bound from 10 years ago just did not correspond to n equals 4 super 8 mils for any value of tau. Because I think they had kind of hoped that maybe it would have corresponded to some special value of tau. Turns out that's just not true. So you could ask, well, what then did their bound correspond to? Like, did it correspond to any physical theory, or is it just maybe just not so strong? So I won't go into detail, but I had a paper with Fernando Alday from a couple years ago where we showed that actually this bound that doesn't have localization, which only assumes basically supersymmetry and crossing symmetry, that bound corresponds to this pure ADS5 supergravity theory, which is basically some conjectural theory that doesn't have any KK modes, and which might have some kind of intriguing connection to this recent work on like the dual of pure ADS3 gravity, because there's some kind of idea that like perhaps you have some kind of like ensemble of CFTs, and like that's exactly what's saturating the bound when you don't put in localization. But I won't go into detail into that. Okay, so you could compute. Yes. This black bound. So this black bound comes from the three non-perturbative constraints. It comes from unitarity, crossing symmetry, and supersymmetric localization. We only get an upper bound. You say why don't you get a lower bound? Yeah. So in general, with the conformal bootstrap, you only get upper bounds unless you put in extra assumptions. The reason why is that with the bootstrap, in principle, the bootstrap allows for a continuum of operators. So like physical theories have scaling dimensions at specific discrete values, but the bootstrap doesn't know that. You're just putting a bound saying I'm allowing operators say at value 5 and everything above 5. And so because of that, you can only compute an upper bound. If you want to get a lower bound, you have to assume a gap in the spectrum. So you would have to say like, oh, there's only say one operator of dimensions less than 4, and then you could scan over the one operator, and then in principle that would give a lower bound. I'll talk about that at the end of the talk. But in order to get that lower bound, your bootstrap has to be sufficiently accurate such that it knows the value of the second lowest operator. Anyway, but I'll talk about that at the end. It's a good question. Yeah? Yes. Yeah, so they basically wrote a paper after we came out with our paper where they said that it violates their religious principles. And so with all due respect to their religion, I don't think it's a scientific argument. Yeah, I mean, it's a very weird theory. Yeah, I mean, look, it's like, I'm not going to put my money that this theory actually exists non-perturbatively. It's just weird that at large, at large end, you certainly have an effective theory. There's no reason why you can't write down an effective theory in ADS. which doesn't have any higher KK modes. That's perfectly kosher. Now, but the statement that this thing would somehow exist non-perturbatively is obviously an incredibly bold statement. I'm not saying it actually does, but one thing which is kind of curious is that even at finite n, in particular for n equals 2, we're finding that this bound is not corresponding to n equals 4 super Gray Mills. And so considering that at large n, we know it corresponds to this pure radius 5, and at finite n, it doesn't correspond to n equals 4, by some kind of continuity argument, you might conjecture that maybe at finite n there is something that's corresponding to it. But I don't exactly know what that is. And so there's some kind of speculation that it has a global symmetry, but again, there's no rules that can't exist. It's we just don't like that, but I don't know. There's a lot of things I don't like that exist.
On its own. Yes. I think when class is pure in this nice doesn't assume that there are no black
I don't really, it's I'm looking at one correlate. So I'm looking at scattering of gravitons, and I'm saying for that specific observable, I find that a theory which I just defined as not having KK modes saturates it. Because that's the only input. I don't want to go too much into detail into that paper, but basically, at large n, you could compute the one-loop correction to graviton scatter. The only thing that depends on is the number of KK modes. And so the claim is that when there's no KK modes, it saturates. If there are KK modes, it doesn't saturate. It's definitely possible. Yeah. Okay, so it's always a question with the bootstrap that you look at one specific correlators, whereas other correlators it could improve even more. But in this case, first of all, the bootstrap, for whatever reason, usually kind of just looking at the correlators, the lowest dimension operators, usually kind of is sufficient. And also the fact that we have, at large n, it's a perfectly well-defined theory, this period is 5 supergravity. And so the fact that that's saturating the bound, it means it can't improve that much because you already have a physical theory that's saturating it. And so that's why I don't think it would change that much, at least at large. At finite n, I don't have a similar proof, but I could just say, from experience that certainly this correlator is not going to improve because we went to very high derivative order. In principle, it's possible with more correlators, maybe it could improve, but I doubt it would improve too much. After all, once you put in localization, you know that it can't improve because it's also being saturated from weak up. Sure. Yeah, okay. So there's also a question of what do I mean when I say saturate? I'm not saying a mathematical statement of exact saturation. I'm saying very, very close. So it's if you look at this picture, you see that this blue line is very, very close to the bottom. But I'm not saying that they're identical. Okay. So here's a similar plot for the OP coefficient. So this plot is a bit more rich in that it's non-monotonic. So it starts at the free theory, it goes down, and it goes up again, which is kind of cool. So why does it decide to go up over here? I don't know. That's kind of a fun fact. So something about this value. Here too, we can also kind of roughly compare it to weak coupling. And in the weak coupling regime, it matches, although it's kind of a smaller regime here. It's a bit less converged. And again, you see that without integrated constraints, the bound would be much weaker. Okay, so that was for n equals 2, but we can run the same thing for larger values of n. So this plot is looking at a range of n. So the x-axis is the coupling, which we now normalize with n, so this is the Tuft coupling, and the y-axis is the same thing, the scaling dimension. And so these different colors correspond to the different values of n. So we start with purple and we go up, so as n gets bigger, this bound is going upper and upper and upper. This black dotted line is the exact value known from integrability, and we're just focusing on the lowest dimension operator. And so the idea is that in this regime, this is the Konishi, but once you hit 4, the lowest dimension operator is now this double trace, which from the perspective of planar integrability is just 4, because it's just 2 plus 2. And so what's something which is kind of fun is that we can see that we're kind of as n is getting bigger and bigger, we're kind of gradually approaching the n equals infinity value. which is kind of like a match to integrability. So here's an analogous plot for the OP coefficient. There is no integrability for OP coefficients yet. I don't have anything to compare to, but you can see it's kind of a similar phenomenon, except now it starts at the top and it's going down. So you can kind of imagine that, my guess is that as n goes to infinity, this is going to turn into some kind of like theta function, like a step function. Which basically has to do with the fact that you have like operator rearrangement between the single trace of weak coupling and the double trace of strong coupling. Okay, so now let's focus on a big value of n, because that's the strong coupling regime, that's what we compare to gravity, that's what we care about the most. So let's put in n equals 10, which as you'll see is big enough. And so we run the same kind of plot. And so just as before, you can compare to weak coupling, which is this blue line, and this matches the weak coupling regime. But now the fun thing is that we can also compare to the strong coupling result, which was that result I had a few slides ago, which was computed just from analytic bootstrapless localization. So that was the answer which was interested in terms of non-holomorphic Eisensteins. And it turns out that now saturates the strong coupling regime. And so this gives even stronger evidence that this upper bound is corresponding to the physical theory. And what's also kind of nice is that there's a little region where neither strong coupling nor weak coupling is a good approximation. And you could say it's this little region over here, which is where you need the numerical bootstrap. Perhaps not the biggest region. And so this is kind of related to level repulsion in some sense, because it's showing how the operator spectrum is rearranging, where it's going from the lowest operator being single trace to being double trace over there. So this is an analogous plot for the OP coefficient. It's a bit more dramatic in that you see a really big change between the single trace regime here at weak coupling and the double trace regime here at strong coupling. And so as I suggested before, we expect that as n goes to infinity, this is going to turn into some kind of like step function. Here's other plots for other values of n, just to show you there's something special about n equals 10. So now we can tell you, if anyone ever asks, like, what is large n and n equals 4 supreme mills, we can tell you. Because you can see exactly for what value of n you start actually seeing the strong coupling regime. Okay, so for the bootstrap experts, this is just because we did some extrapolations in the derivative order, so this is just to show that they make sense. Yeah. This one? Or yeah, so there's all kinds of games you can play with resumming things. The weak coupling ped A just meant that we have a for loop result at weak coupling, and we just do a ped A, which seems to match a little bit better. We don't put in strong coupling because the strong coupling is also like large n finite tau, whereas the weak coupling it's just depending on G and Mills, not even depending on tau. So that's why it would be a little bit funny to try to combine the two. I know there was these old papers by I think Ashok and Rastelli where they were trying to do stuff like that, but we didn't try that. Okay, so finally about n equals 4 before I move on to ABGM. One of the goals of this program is to fix these higher derivative corrections, as I discussed before, because the idea is that the first couple higher derivative corrections, r to the 4 and d to the 4, r to the 4, we know exactly, but the goal is to get these unprotected corrections, like d to the 8, r to the 4. So our first step in that direction is here. So here we focus on this large value of n, and we also focus on the strong coupling regime. And so this brown line is the numerical upper bound. This dotted line is just the old bound by Rastelli. And then these colored lines, these are the analytic predictions, which were computed from analytic bootstrap and localization. And so, for instance, so it's the scaling dimension, the OP coefficient. So you find that the purple line is a horizontal, sorry, not the purple line, the green line is a horizontal line because that's the supergravity term, and that doesn't depend on the coupling. So that's like pretty close, but it could be closer. And then we add the first correction, which is this red line, which is basically just as far away. Now it depends on the coupling. But then when we add the next correction on top of that, we finally get the purple line, which is even closer. And it's even more dramatic for the OP coefficient. So it does seem that as you add more 1 over n corrections, you are getting closer to our claimed non-perturbative result, which kind of gives the hope that perhaps in the future, with greater precision, we might be able to start reading off some 1 over n corrections. Although we're not yet at that point for n equals 4. We will be for ABGM, as you'll see in a moment. Okay, so that's all I'm saying about n equals 4. Now we can move on to ABGM. So in 3D, all 3D n equals 8 CFTs have S2 global symmetry, and all the known theories are these Chern-Simons matter theories, as shown by Daniel and others back in 2008. So they have 2 gauge groups, Chern-Simons level K. We want to talk about maximal supersymmetry, and so in that case, we're going to fix K to be 1 or 2, and the difference between these gauge groups can only be 1 or 0, because the other cases would have reduced supersymmetry. So another fact is that these theories, when k equals 1, are actually product theories. Between a free theory and an interacting theory, we only care about the interacting one. So this theory is strongly coupled basically for all values of n except for n equals 1. So it's even harder to study than n equals 4, because like there's no weak coupling limit when you have maximal supersymmetry, which is related to the fact that it's dual to m theory. And so we're going to parameterize this theory by the stress tensor two-point function coefficient, C, which is proportional to n to the 3/2. So again, we look at the stress tensor multiplet 4-point function. Again, we look at the superprimary. We can expand in blocks, just as before. Again, there are both short and long multiplets in this correlator. The novelty of 3D versus 4D is that in 4D, the short multiplets were all trivial because they didn't depend on the coupling. Whereas now in 3D, the short multiplets are non-trivial in that they do depend on the coupling. So even though their scaling dimensions are fixed, their OPE coefficients are non-trivial. And that's one of the big differences between this bootstrap and the previous one. And so in particular, you have two kinds of protected multiplets. You have these B's, which are the half BPS, and then you have these A multiplets. You have them for every spin, and these are like less than half BPS. And so what's nice about having these protected multiplets that are non-trivial is that you can compute both upper and lower bounds. And the reason why is that their scaling dimensions are separated from the continuum of long multiplet scaling dimensions. And so that allows you to compute both upper and lower bounds without any assumptions. And so that's another advantage of this 3D bootstrap versus the 4D. So we have localization constraints, just as we had in 4D. So again, we consider the sphere free energy deformed by a mass. Mass couples to the stress tensor multiplets. You can take derivatives to get a relation between the 4-point function and these derivatives. It turns out there's two independent relations, which we show here. It turns out that one of the relations actually is particularly simple because the integral trivializes and it ends up just being written in terms of these two protected OP coefficients. And this is due to there's some kind of 1D topological theory which explains that. You can also compute CT non-perturbatively by taking two derivatives. And finally, one last non-perturbative constraint is that this 1D theory implies a relation between these protected OP coefficients. So basically, at the end of the day, you could compute all the short multiplets exactly using localization, which is B plus, B2, as well as the stress tensor multiplet. So just as before, the reason why this relation is useful is that the sphere free energy can be computed non-perturbatively using localization. And so it equals this hideous function here, although it's actually less hideous than the 4D case because there's no instantons. And so that's a huge simplification. And so this is just the full answer. So there's been a lot of wonderful work done on this. So originally people studied it at large n, and they showed how they could compute this quantity to all orders of 1 over n for any values of the mass in terms of this airy function here. And then more recently, there's a beautiful work by Nosaka here in China, where he showed how you could compute this quantity exactly for every value of mass. So this goes beyond the 1 over n expansion. So we just have a complete non-perturbative expression. The answer is written basically in terms of pies for this quantity for any value of mass, for any value of n, for any value of m, and for any value of k. So I think this is a remarkable result, which I always try to advertise, because like it's very rare in quantum field theory that you compute a quantity totally non-perturbatively. They won't let you out. You're forced to stay for the talk. Yeah, so it's very cool that you can compute this thing completely exactly. Okay, so before we talk about the numerical bootstrap results, let's talk about some strong coupling results. So again, you could use analytic bootstrap to study this theory in a 1 over n expansion. Just as before, we get the similar kind of expansion. So this is the supergravity term, higher derivative correction r to the 4, 1 loop, etc. These terms were computed in a series of papers by me as well as others. And then you can fix two of the coefficients at every order of 1 over n using localization. And so that means from the analytic bootstrap perspective, we know CFD data up to d to the 6 r to the 4 order. So this is an example of a certain CFD data. So this is one of these semi-short multiplets at spin 0. Recall that it's non-trivial. This is the supergravity. This is generalized free field theory. This is supergravity. This is 1 loop. This is d to the 6 r to the 4. It turns out r to the 4 doesn't contribute to this quantity. And so this is everything we kind of know exactly a priori, which we can use to compare to the bootstrap. But if we want to go beyond d to the 6 r to the 4, this analytic bootstrap is insufficient. So as I discussed before, you need the additional input of unitarity, i.e. you have to work at finite n, i.e. you need to use numerical bootstrap. And so that's the thing we are going to discuss next. Yeah, so if you can actually compute this thing in closed form. It ends up being like pi squared plus pi to the 4. And we guessed that kind of later. Yeah, but there is a closed form answer. Yeah, I will say, like, computing this quantity was a heroic calculation. It's very, very hard. Okay. This comes from two things. So to compute this one loop term, first of all, you have to compute the one loop term in supergravity, which we compute using this method invented by Fernando, Agnese, and Ofer, which is kind of this like one loop ADS unitarity method. But then there's also a contact term ambiguity, which isn't fixed by that method, and for that you need localization. And so it's only by combining all of this together that you get this number. This number you got from localization. This you just got from usual analytic bootstrap. Okay. Okay, so now let's move on to numerical bootstrap. So I've been bootstrapping ABGM for many years. In fact, my very first paper in grad school was bootstrapping ABGM. So what exactly has changed over all these, unfortunately, many years? So this plot kind of summarizes that. So in earlier work, we combined the usual bootstrap, and we were also able to put in one of these localization constraints. Because remember, there's two localization constraints. One involves an integral and one doesn't. Because one of them simplifies due to this 1D theory. So in the past, we had imposed the simpler one, which was the one which is just written in terms of OP coefficients. And that gave you this light orange region here. And this plot, I'm comparing CFT data of two semi-short OP coefficients. So we got an island before, because you always get an island, just because these operators are separated from the continuum. And it was a pretty small island to begin with. I mean, as you see, the x-axis, the y-axis are pretty narrow. But we can get an even smaller island after putting in the second localization constraint, which is the integrated one. That required this new technology of imposing integrated constraints, which took a while for us to figure out. And so as you see, the island shrinks by a factor of 100. And so this really shows the power of these localization constraints. Because it's like, yeah, now the island is truly tiny. In fact, like I would say the island now is, on a similar level of the island found for the Ising. Which perhaps isn't so surprising, because after all, this is also a 3D theory. In some sense, it's simpler than the Ising model, so you have all the supersymmetry. Cool. Okay, so we can get these incredibly small islands for every value of n and for k equals 1 and 2, which are the two cases of maximal supersymmetry. So now, what can we learn from these incredibly tiny islands? And also, just to reemphasize, we're getting islands now. Whereas at n equals 4, we had an upper bound, now we get an island. So that means we have rigorously determined the values of the CFT data. So one thing we'd like to do is we'd like to look at the theory at large n and see if we can learn about higher derivative corrections. So that's what we're going to do here. So the x-axis is 1 over n, and we're looking at the regime where n's really big, which is why these numbers are very small here. And the y-axis is the result we get for the CFT data, for the semi-short operator. The right plot left plot is k equals 1, the right plot is k equals 2. And so this little black dot here is the upper and lower bound we got for n equals 10 in particular. And so as you can see, it's very, very small. So this is a rigorous upper and lower bound. It's so small that you can barely even see the difference between the dot and the upper and lower bound. And then what we can do is that we can compare our rigorous non-perturbative estimate to this large n expansion that was computed previously. And so that's what these colored lines are. So green is the supergravity correction, and then red is the one loop correction, and then finally blue is adding in this d to the 6 r to the 4. And lo and behold, we find that it exactly is within our allowed region. And so this is a very satisfying result because first of all, computing these analytic corrections was incredibly complicated, and it shows that we didn't make any mistakes because we matched this completely independent calculation on the nose. And it also shows that the bootstrap is sensitive enough that we're actually sensitive to this incredibly high order correction. So the results in 3D are way more powerful than 4D. Because in 4D, I showed you this plot when we were trying to compare it to stringy corrections, and it was still a bit kind of vague. Whereas here, we get an incredibly precise match to the highest order correction that has been computed so far, which is this d to the 6 r to the 4. And we get this for two different values of k. So there's kind of two independent checks. The reason why there's two black dots here is that when k equals 2, there's actually two different ABGM theories. There's ABJ and ABJM. They basically differ by the gauge group. But they all work, as you see. And you can also do this for other values of n. This is n equals 10. You can do it for n equals 9, n equals 11. It continues to work. Okay, so that's already was very exciting for us. But turns out you can go beyond d to the 6 r to the 4. So the ultimate goal of this program is to learn about unprotected data. So we can truly learn about non-perturbative string theory, non-perturbative M theory. I mean, that's the goal. And so that's what we're going to do next. So in some sense, this bootstrap bound, while precise, wasn't precise enough. Because if the bound was even smaller, then you would have found that the blue line would have been outside the allowed region, implying that you are sensitive to the correction after d to the 6 RD. And so it turns out there's a different CFD data, which turns out to be even more precise than spin 0. In general, kind of the lower spins are the more precise ones. But it turns out A2 is more precise than A+, for whatever reason. And so for this CFD data, when you compare our bootstrap upper and lower bound here to the analytic prediction, you find that even after including d to the 6 r to the 4, you get a blue line which is outside the allowed region. And so that means we are sensitive to the next correction. So it's kind of good that it's outside the allowed region. And so then on the right-hand side, we compare the difference between the analytic prediction and our rigorous numerical bound. So this is the residual, and particularly we do a log-log plot. And the reason why we're doing a log-log plot is we want to predict what is the power of n for the next correction beyond d to the 6 r to the 4. Or to be more precise, what is the power of c? And so from M theory, we expect the next term should be d to the 8 r to the 4, which should have 23/9. And lo and behold, we learn from this rigorous numerical bootstrap that the next correction is 22.3 plus or minus 0.5. So it is consistent with 23/9. So that's kind of the first, rigorous, interesting prediction, that we actually find a non-zero d to the 8 r to the 4 correction. Which itself, I will say, is somewhat surprising, because there are people in the literature who claim that d to the 8 r to the 4 would be 0 for M theory, and so we have disproven that. Okay, so, and we did this for both k equals 1 as well as k equals 2. Here I'm just showing k equals 1. We can go beyond this. So now we can, instead of deriving the value of this power, we could just assume it's 23/9 and then read off the coefficient. And so that's what we do here. We do it for both k equals 1 and k equals 2. We get this very rough estimate. And there's actually a check on these numbers. Because we know from dimensional analysis that when you compactify M theory in 84 across 7 mod ck, this contact term of d to the 8 r to the 4 should come with a certain power of k. That just comes from dimensional analysis. And it's k to the minus 14/9. So that means the difference between these two numbers should be 2 to the minus 14/9. 2 to the 14/9 being 2.9. And indeed, the ratio between these two numbers with the error bar is consistent with this value. So of course, these things are still a bit rough, but to me, I find it very cool that we are really matching this incredibly non-trivial prediction. I mean, the ratio could have been 1 billion, and it turns out it's consistent with 3. This is d to the 8 r to the 4 in ADS, yeah. Oh, okay, that's an excellent question, and I'll talk about that in a minute. So maybe I shouldn't be too critical of that conjecture. So Tsongkhao raises an excellent point, which is that right now we are computing the contribution of d to the 8 r to the 4 to a specific CFD data. Now, say we want to know what d to the 8 r to the 4 is in flat space, for the 11-dimensional M theory S matrix. So there is a way of going from graviton scattering in ADS to flat space. There's this flat space limit derived by Penedonis. And so the idea, which was first worked out by me, Shai, and Silviu in a paper 8 years ago, is that you first compute the ADS scattering, and then you take the flat space limit, and that teaches you about flat space scattering. And so in order to fix the full d to the 8 r to the 4 term in ADS, there's kind of 4 coefficients you have to put in, because analytic bootstrap fixes it up to 4 numbers. 2 of those you can put in analytically using localization. A third you can put in numerically, because we fixed this one specific CFD data. And so we need to numerically compute 1 more CFD data, and then we'd be able to fix it and take the flat space limit and rigorously prove that in flat space 2, it is also non-zero. Yeah, so we're not there yet. So Tsongkhao raises an excellent point. I think we will get there soon. We just need to find another CFD data for which we have very accurate islands, which is something we're working on at the moment. But I strongly suspect we'll be non-zero. Because otherwise it would require some kind of very non-trivial cancellation. Okay, so in conclusion, we have combined bootstrap and localization to give a non-perturbative solution to holographic CFTs at finite n and coupling. It's kind of fulfilling the dream of ADS CFT. And so in particular, for n equals 4 super-Yang mills, we have evidence that our upper bound is corresponding to physical theory by comparison to both weak and strong coupling. So for n equals 4, it's still a bit conjectural because we don't have a rigorous lower bound, just an upper bound. For ABJM, our results are much more powerful because we have rigorous both upper and lower bounds, i.e. we have islands. And there we find that these islands are completely consistent with the strong coupling expansion to the highest order that people computed, which is d to the 6 r to the 4. And in fact, the bounds were so accurate that we were able to start learning about higher derivative corrections. And in the case of ABGM, we could even read off the first unprotected correction, d to the 8 r to the 4. And so this is the first example in the literature of studying unprotected data in M theory, because there is no other method that can do this. Okay, so there's many future directions to this program. So of course we want to get more accurate bounds, which will give us access to more data. So how can we go about doing this? So one way would be to derive additional localization constraints. So in addition to taking derivatives of a mass, or tau, there's another thing you could consider, which is you can squash the sphere, and it turns out there's only one way of squashing the sphere. It's parameterized by one variable, which is called b. So you can take derivatives of this b and then set b equals to 1, and this b couples to the stress tensor multiple. And you could also compute it using localization. So it turns out that in 4D, this doesn't give any new constraints for the 4-point function, and this is based on a paper I'll be coming out within a couple of weeks. So in 4D, it's a bit disappointing. But in 3D, we are still hopeful that it might give a new constraint, and the reason why we hope that is because localization in 3D requires less supersymmetry than 4D. It only requires 4 supercharges as opposed to 8 supercharges, so that gives us some intuition that there might be more power in 3D. So 3D is always better. So another way that we might be able to improve our bounds would be by doing mixed correlators. So this is a common strategy in the Bootstrap. For instance, in the icing model, the original paper had just an upper bound with a kink, and they only got an island by doing mixed correlators. And so usually you gain by doing mixed correlators of other operators that have very low dimensions. Usually if you do mixed correlators with very high dimensions, it barely affects the results. So far, we've done a single correlator of the stress tensor multiplet, whose superprimary, has dimension 2 in 4 dimensions or 1 in 3 dimensions. So what are the other low-lying operators? So in 4D, there's just one other low-lying operator, which would be the Konishi, which at least at weak coupling has dimension around 2. And so I expect that if you do a mixed correlator system between this Konishi as well as the stress tensor multiplet in 4D, that will hopefully improve the bounds. It's very challenging to do because this is a long multiplet, it's unprotected, so that means there'll be like many crossing equations, and so it's basically a technical barrier. But I'm hoping with this new Bootstrap technology that might be possible. You could do a similar thing in 3D in principle. Now I think there'd be like 2 different low-lying operators, so it'd be a bit more complicated, but it should also be possible. And so kind of like the motivation for doing this, the most immediate thing is to be able to, answering Sungkow's question from before, is to fix another CFD data to sufficient precision such that we can read off its d to the 8 r to the 4 term. And so I think this is kind of the candidate CFD data because this is the most accurate one so far. And then we'd be able to really derive the M theory S matrix at d to the 8 r to the 4. In the case of 4D, the first goal we want to do is to be able to get islands instead of just upper bounds. And so the way we would do that, as I kind of mentioned before, is that we would put some gap to 4 and assume there's only a certain number of relevant operators. So in general, you expect there to be 2 because there's kind of like a double trace operator and a single trace operator. And if the Bootstrap is sensitive to the next lowest operator, then you should be able to get lower bounds as well. It's not yet sensitive enough, but that's something we would like to do in the future. Okay, so in addition to n equals 4 in ABJM, I want to emphasize that this is a very broad program. So the methods we used can be applied to any theory in which you have localization. And so this in particular applies to any 3D n equals 2 theory, any 4D n equals 2 theory, or any 5D n equals 1 theory, as long as you have some kind of Lagrangian that you could write down. And there's even some non-Lagrangian cases where you can do something. So for instance, there's already been some results for a certain 4D n equals 2 gauge theory, which is basically dual to open strings. So this is like my favorite theory in the last few years. It's basically a theory which has flavor brains. So it has these D7 brains in addition to ND3 brains. And so you can study both open string scattering as well as closed string scattering, but all the same methods apply. You have localization, you have integrated constraints. And so I've had a series of papers about that, doing both analytic as well as numerical bootstrap. You could also study ABJM for general values of K. So now the supersymmetry is slightly less, it's n equals 6. But this is a very rich family of theories because depending on the value of K or N, there's basically every theory of quantum gravity appears in this family of theories. Because you have string theory when K and N are both big, you have M theory when N is big and K is finite, and then you even have this higher spin gravity if you allow the ranks of 2 gauge groups to be very different. So in principle, you can interpolate between every theory of quantum gravity. And so we kind of initiated the numerical bootstrap of this more general class of theories a few years ago, but we didn't put in integrated constraints. And so that's something we want to do for the future. We're also deriving more integrated constraints. The most ambitious goal of this program, which is kind of our long-term goal, is not just to fix higher derivative corrections, which itself is very nice, but would be to be able to access high twist operators. Because if we can access operators with very high dimensions, these operators are dual to black hole states, because they have very high energy. And so imagine in the future, if we can read off, say, the 10 lowest operators in ABGM theory, non-perturbatively as a function of n and k. And we could do this changing the value of n. So then, as n gets big, we should enter the gravity regime, and there should be some conceptual predictions from quantum gravity of the statistics of black hole states that should appear in the scattering of gravitons. And this should be different from what you would see, say, at very small values of n, in which case you don't have this Einstein gravity regime. And so this is kind of the long-term goal, that we should be able to kind of study things about quantum black holes non-perturbatively. And to me, this would truly be solving, quantum gravity. Yeah, that's for the future. Right, that's it.
Yes. What about 6D Tokamadera series?
Okay, so that's an excellent question. So there's been some work on 62,0. So like the original work was by Rosselli and collaborators, also roughly 10 years ago, where they did numerical bootstrap for 6D. And so you could ask, can you improve that with some additional constraints, something analogous to localization? So you don't have a Lagrangian in 6D, and so you don't really have localization. There are some tricks where for certain observables in 6D, you could do localization in 5D, super Yang-Mills, and so you could think of like 6D compactifying one dimension on a circle, and then by studying some things in 5D, you can then go back to 6D. But this only computes very specific observables. So this allows you to compute, let's say, like the index of 62,0. But that method, as far as I know, is insufficient to compute the sphere free energy in 6D. Another difficulty of 6D is that you don't really have the analog of a mass. And so there's no notion of like the mass to form sphere free energy. So what you do have, this just follows from group theory in 6 dimensions. So what you do have is you do have squashing. So you can compute the squash sphere in 6D in principle, and derivatives of that squash sphere would be related to the stress tensor correlator, although I'm pretty sure that those constraints ended up being trivial. So I think there was some papers, maybe even by Daniel and I think other people, where they discussed how, I guess, this taking derivatives of the squash sphere just kind of gives you the values of protected quantities that you already knew. And so I don't think it would give a new constraint. Now, so there's another thing you have at 6D, which is the 2D chiral algebra. The 2D chiral algebra is basically a sector of the 6D theory that only describes certain protected operators, and within this sector you can compute everything. There's kind of an analogous story in 4D. But 6D is kind of more interesting because the 2D chiral algebra for n equals 4 spring Mills is trivial, and so it just tells you stuff that you already knew from the free theory. Whereas in 6D, it's non-trivial, and that it computes OP coefficients of protected operators that are non-trivial functions of n. And so I had a paper with Eric Perlmutter like 10 years ago where we used that analytically for the analytic bootstrap at large n in order to fix this part of the forward correction. And so it's possible that we could also input that data into the numerical bootstrap in order to improve it. This is something I had tried some years back and just didn't improve it very much. But this is also a long time ago, so it could be interesting to revisit that.
Okay. Question is, have you tried adding dispersive functionals to when deriving these bounds? I guess you're using this Euclidean expansion. Have you tried adding dispersive functionals?
Okay, yeah. So dispersive functions would be like another way of sampling crossing symmetry in some sense.
Yes.
So the idea, like, for those less familiar, is that you have these crossing constraints, which are like these, whole functions worth of constraints. So it's a massive constraint. And so you have to truncate it somehow. So the usual approach in numerical bootstrap is that you basically truncate this function by doing a Taylor series around some special point. There's another approach, which is these dispersive functionals, which samples like a different regime of this function. And so these dispersive functionals, I guess, have been useful in kind of relating, I guess, like the integrability regime of like very large lambda to, I guess, the regime of 1 over n and 1 over lambda. So yeah, we haven't looked into looking at dispersive functionals. I somehow suspect that wouldn't improve things too much because, like, I feel like we're already kind of maximally taking advantage of crossing symmetry for this specific correlator. And the reason why I say that is that as we increase the derivative order, the bounds aren't improving. No, but I mean, it could be though that like maybe they won't improve in this basis, and maybe if you dispersive functions they would have. So it's always possible. Yeah, Yeah, so yeah, it'd be interesting to try. Although it'd be interesting to try that maybe even for the Ising model. I mean, like, just for, any theory.
The second question is that, so for the correlators that you consider in these multiplets, they contain the 2-point energy correlator, which is positive and extra constraint. Follow from what you used.
Wait, sorry, say it again?
So there is this ANEC, right?
Yeah.
Now, if I take these 4-point functions that you have,
Yes.
they have stress tensor in the multiplet.
Sure.
So then I can compute the energy correlator using your functions and impose that it has to be positive, which is ANEC. And it's
You're saying, so this is an extra constraint on the 4-point.
yes.
Interesting. And so this
It could be that it's useless.
Is this a constraint that in principle follows from crossing symmetry, or is it something in addition to that?
Well, it seems a bit in addition. It's ANEC.
Okay. Well, yeah, yeah, it'd be great. Yeah, I mean, it'd be very cool if that could give better bounds. I guess this is something which you're saying is a very general statement. So like this should apply even to the Ising model.
But then you need to, then the stress tensor is not related to
So I see. So you're saying, so the advantage of having supersymmetry is that you could apply this to one of the correlators we're already studying, which are just like scalar correlators. I think it's a very interesting idea. Yeah, to be honest, I haven't really thought about that, and I don't know how to impose it. I'm assuming this would probably be related to an infinite sum of CFT data. And so there'd be some kind of, but I guess it's maybe analogous to integrated constraints. So like the same way with integrated constraints, you're basically taking some like average of infinite data and saying they have to equal something. So to this ANEC constraint would be like a different average.
Yes.
Yeah, that could be interesting to think about.
Maybe one more quick question. Yeah.
Can you see anything about the discreteness of n from the bootstrap point of view? Of course, I know from localization, discrete n is built in, but if you would imagine you extrapolated those functions, do you see something special at integer n?
That's an excellent question. So I think it's one of the outstanding questions in, I guess, this holographic bootstrap program is like, how do you impose the value that n is a discrete thing? And the answer is I don't know. So I mean, I guess that would be another constraint in principle that one could try to demand. But I have no idea how to do it.
If there's no question, let's thank the speakers again.